Thank you everyone for coming to today's USRC Tech Talk. My name is Stephen Holes. I'm the Assistant Project Manager for the University Innovation Project. For those who aren't aware of what the University Student Research Challenge, USRC, is, it's a program that seeks to challenge students by inviting them to propose new research ideas that can help solve some of the biggest technical challenges in modern aviation. And some of the proposal teams are selected and awarded grants to pursue their ideas. Today, we have the AVIATA team for you, presenting their work from their USRC project. But just before we start, just a few housekeeping rules. If you have any questions during the presentation, please type them in the chat or wait until the Q&A portion, and we'll call on you or your question after the presentation. If you want to be put on the future invites for USRC Tech Talks, please fill out the sign-in form on the chat or send me an email, which is also in the chat. If you would like to see this presentation later or see any more information about the USRC program, please see our website as posted. And I will hand it over to the USRC team to go ahead and get started. Thank you.
Excellent. Thank you, Stephen. So firstly, hi, everybody. Thank you all for being here and for attending our presentation. We're really looking forward to sharing our progress and our results with you so far. I'd like to quickly mention that unfortunately, David Thorne could not be with us today. He was originally planning to present alongside Ryan and I, but one of our team leaders, Brugu, will be taking over for him today. So a little bit of background about us. We are a part of UAS at UCLA. It's an undergraduate student organization at UCLA focusing on unmanned aerial systems. And the project that we're presenting as part of USRC is called AVIATA, which stands for Autonomous Vehicle Infinite Airtime Apparatus. And before we get started, we'll go ahead and introduce ourselves. So my name is Axel. I was a fourth-year computer science student this year.
My name is Brugu, and I was a senior mechanical engineering student this year.
And my name is Ryan. I was a senior computer engineering student.
And we'd also like to acknowledge the rest of our club members, as well as some of our advisors and alumni who also participated in the project in various ways and contributed to the results that we're about to present. Unfortunately, not all of them could be present today, but we'll certainly be sharing this recording with them. And so at this point, we'll go ahead and head into an overview of the project. So the objective of the AVIATA project is to construct a swarm of 8 rigidly attached drones. These drones mechanically attach and detach to a central frame, which you can see on this poster here, and they work together to carry a payload. And the neat thing about this is that the system can fly with less than 8 drones, so that drones that are low on battery can be switched out while the system is flying for drones that have a fresh battery. And so in theory, the system could fly as long as fresh drones are available to take over. Possible purposes for such a system could be to be able to carry more weight using smaller and more adaptable drones, as well as being able to carry items for longer, such as things that need to stay airborne for longer than a single drone would be able to carry them for, such as, for example, a temporary cell tower. And then during our design process, we developed several mission requirements to help guide our development. So AVIATA consists of 3 components: a purely mechanical frame onto which detachable drones attach, and the third portion is a stationary ground station. The frame holds up to 8 drones, and drones will be able to dock and undock completely autonomously. And then the system as a whole will be able to navigate using waypoints given from the ground station. And the system will be able to carry a 2-kilogram payload with at least 6 out of the 8 drones docked at a time, which means that 2 drones can engage in the docking and undocking procedure at a time. And then in terms of how we organized ourselves,
oh, sorry about that. There you go.
Yes, thank you. In terms of how we organized ourselves, we broke it down into 4 main sub-teams in order to address each of the major issues more accurately. So the airframe team was responsible for the mechanical engineering of our unique structures. The control sub-team was in charge of handling stable flight control of rigidly attached drones, which affects the control of flight. Communications was in charge of facilitating information transfer by administrating a network for the drones to communicate with each other on. And finally, the docking team was in charge of designing and implementing a docking process for drones to be able to switch in and out of the system autonomously. And then a brief timeline of some of our work over the past year. Our proposal was accepted in July of last year, and we completed crowdfunding in October, during which we raised just over $2,700. In October as well, we had our preliminary design review where we invited professors and alumni to review our initial concepts for AVIATA. And we used that feedback over the latter portion of last year in order to complete our early designs and simulations by December. That enabled us to purchase major hardware in January to start physical testing, and we presented some of the early results of those physical tests during our critical design review in February. And ever since then, we've been doing a series of design refinements and more testing, and we achieved some significant milestones in May where we were successfully able to fly 4 rigidly attached drones, as well as complete a stationary docking test, which we'll be showing. And here I'll let Brugu go into more detail about the mechanical engineering portion.
Hello, I'm Brugu. I'm one of the airframe directors of UAS, and I'll be talking about some of the airframe parts of this project. So the role of the mechanical and airframe team is essentially to create the physical swarm system that the controls and software team are going to be interfacing with. And so our primary objective is to make it as robust and simple as possible, given that the controls and docking implementation are the most nuanced aspects of the projects that we want to let shine. So the main aspects of our project are the octocopter frame, which is the central frame which holds the payload, and it has allows the drones to dock at the end of each of those spokes of that frame, and the docking mechanism, which allows drones to mechanically dock and undock from the frame using APRIL-tag identification tags. And we're doing this using commercial off-the-shelf drones that we're modifying with the docking mechanism underneath. So this is the overall central frame of the system. So this in the center is 2 carbon fiber plates that are sandwiching those 8 square tubes that come out of the center. On top of those carbon fiber plates is that large APRIL tag target that's used for the first stage of docking. And at the end of each of those tubes is a docking joint with a sort of cone section and a cylindrical section. The cone section allows for a little bit of tolerance in the alignment by the docking team, and in the cylindrical section is the platforms necessary to perform the actual docking. We'll go into more detail about that a little bit later. Underneath those central plates is a payload box where we can insert our 2-kilogram payload. Our goal is to have the entire frame be unpowered, so no batteries or anything is required for that part of the system. All of the powered components will be attached to the drone itself. Sorry about that, just had to clear my throat. So for the we performed a 4-drone test earlier this year, which we mentioned, and for that we manufactured a separate drone. So essentially it has a 3D printed central mount and 4 symmetrical booms coming from the center. Those ones are the same booms we're planning on using in the final design. And all of the drones on the periphery are rigidly attached to that frame. So it's different than their final design in that the drones cannot dock and undock, but it provides a useful tool for the controls team to be able to do control a multi-drone system. And we'll discuss the results of that later on this quarter, or later on in this report. So here's a docking mechanism we had previously designed for our up to our CDR, essentially. It has these 2 funnel-like structures which would be attached to the frame, and the rack and pinion structures would be attached to the drone itself. 2 servos would actuate those pinion gears to push those racks into those funnels, and that was our previous method of docking and alignment as well. We had some success with that, but upon some review from our critical design review and advice from professors and whatnot, we decided to switch to a different design, one that had less mechanisms of failure and was generally simpler in design. So in this next slide, we see the sort of the current docking mechanism we're planning on using. So you see the bottom structure has a large cone which again, as I mentioned before, allows some tolerance and alignment so that even if you're off by a little bit, you should hopefully slide into the proper orientation. There's a alignment feature at the bottom of the docking mechanism that's attached to the drone itself, which corresponds to another sort of recessed alignment feature in the bottom of this cylindrical section, so that as you yaw the drone, you should drop into that recessed hole. If you see in that animated GIF on the top left, there's essentially a linkage that connects the servo horn to 4 separate keys. And as that rotates 90 degrees, the keys are inserted into the 4 platforms of that docking mechanism. And essentially do that same process in reverse to undock from the system. And at the bottom of that alignment feature that I mentioned earlier, there's actual a metal contact at the bottom of the cylindrical section that connects to, essentially completes a circuit within the drone that confirms that docking has been successful. But we'll discuss that a little more later on. Finally, we generated a risk matrix for the system. So this risk matrix on the right, the horizontal axis is the severity of the failure. So left is least severe, right is intolerable severity. And then the vertical axis is the likelihood of the failure. So less likely on the top, more likely at the bottom. And so we rated some of the subcomponents of our mechanism or our system using this risk matrix. So the coupling of the docking mechanism, we rated an 8. Coupling means the ability to either successfully dock or undock from that system. So if there's a failure in that, it could be a pretty significant, cause a pretty significant impact on the performance of the system. But we decided that because there are 8 other potential docking points, or 2 other ones that could be used to fly with the payload, it's not necessarily a catastrophic failure because there's sort of a backup. We decided the same risk was present in the strength of the docking mechanism. So if that joint mechanically fails, then essentially has the same risk of knocking out one of the potential docking joints. For the frame strength, we have sort of a lower risk because it's less likely to break, although the risk if it did break would be essentially the same as one of the docking mechanisms no longer being available, along with a few other complications for the controls team to deal with. Then we have oscillations in the frame. This is something that we did end up seeing and we will discuss later on, but it's not, with some of the software changes we made, it should not be a super likely event that the drones on the end cause oscillations in the frame. The thrust of the drones should be sufficient to fly in most conditions, so we don't believe that's going to be a super high risk factor. And the aerodynamic impact of that large central APO tag, we don't believe will be a very large risk factor either. Finally, we have some future considerations for our airframe. One, you may have noticed that those docking joints at the end of the frames are quite large. So reducing the size of those is one of our main goals. The reason it's so large is because we want to provide as much tolerance or leeway as possible to the docking team to do that alignment via the computer vision system. But there's still a lot of room to reduce that size and weight. We also need to check its robustness in flight to make sure that the drones don't slip out during flight, essentially. Increasing the frame strength, we have a few concerns about the strength of the central frame, which we think could be addressed with either adding some additional support beams or potentially increasing the size of those booms that come from the center. And also, we'd like to perform some more aerodynamic testing of the entire 8-drone system or 6-drone system in flight. And now I'll pass it on to Ryan to discuss the controls aspect of this project.
All right. Hello again. So I will be talking about controlling this rigid frame of multiple vehicles. So that's the goal of controls. And this involves managing how commands and telemetry are communicated. And another part of this is creating a motor control allocation and tuning the controller. The way we're implementing this in software is by modifying the stock PX4 flight firmware that is available for many flight controllers. And we're also using a Raspberry Pi on each drone for some specialized tasks. We have additional goals for autonomy of the system when it is finally built, such as swapping drones out when appropriate based on battery levels and ensuring that the frame is always in a flyable state, as well as handling failures appropriately. This project is for the ARMD strategic thrust for assured autonomy, and so that is important. However, you do have to walk before you can run. So what we've been focusing on in this project for controls is the base requirement of flying a rigid structure with multiple vehicles attached to it. And so that is certainly a challenge in and of itself. So we'll get into that. So the approach we're taking to this is starting by looking at the frame as a single vehicle, where the locations of the rotors and the properties of those rotors are what characterize how the vehicle flies. And so we want to think about the physics that are going on here, where you give each motor some command for some speed, and that results in a resultant torque and force on the entire rigid frame. And so whether it's multiple vehicles or one vehicle, the way you control something like this is by inverting those dynamics and deciding, well, how are you going to actuate your motors to accomplish your goal torque and your goal force? And when we're thinking about that, we also have to think about the entire control system for the vehicle. And so this is just showing a standard control system for a multicopter. And the very last step that says mixer there is the control allocation that I was just talking about with deciding how to actuate your motors. And then before that are all these higher level controllers, such as attitude control, and that goes all the way back to position control. And so essentially this is showing the process by which you control position on a multicopter. To simulate the physics that are going on here in a very ideal way, albeit we did write our own simulator from scratch, and we used Python for this. So it is nothing super advanced. Unfortunately, we didn't have a whole lot of time to look into other more existing robotic simulators in the industry and modify those to our needs. So right now, this is what we have, and it is simulating probably the most ideal physics you possibly could have. And so there's obviously room to add disturbances, but what feedback we do get right now is the motor thrust. So it's showing the locations of each rotor on the frame, and it changes color based on how much thrust. So more red for if the motor is getting a faster motor command, and more blue if it's spinning slower. And here we've implemented a position control similarly to how it is implemented on the real flight controller. So here is a video of that, and I'm just moving around the orange dot with my keyboard arrow keys, so very simple, and the drone is using its position control to find it, or to go follow it. I'm also manually just making drones disappear and reappear like magic. So obviously it's like magic in here, it won't be in real life. But what it does accomplish, though, is showing that the system is flyable in several different configurations. So let's go back and revisit the motor allocation I was talking about. So this is showing some screen grabs from the simulator hovering at rest. And so these are these two screenshots are for identical systems. There are 3 drones that are undocked or missing on the right side of the frame. And this is quite a lopsided configuration of drones, and it's probably unlikely that we would fly in this state, but it does kind of demonstrate how big of a difference there could be between motor control allocations. So on the left is standard mapping from essentially your torque and force commands to your motor commands. And it uses the Moore-Penrose pseudo-inverse of your linear dynamics, and that's certainly not something you have to understand for now if you're not brushed up on linear algebra. But it is a relatively standard way to get your inverse dynamics to generate your mapping to your motors. On the right is one where we've optimized to be able to achieve the highest maximum thrust. And a way to look at this is if you see on the left, some of the motors on the right side of the structure are a little more red. It is a subtle difference, so I'm sorry if it doesn't come across on the screen. But on the right, the total redness of the motors is a little less, meaning that the motors with the highest that are being commanded to spin the fastest are a little slower, and the ones that are in bright blue there are getting a command to spin at 0 speed or generate 0 thrust. And that's simply because this configuration is so lopsided. It's decided that those motors are basically doing more harm than good if they were to generate thrust. And so it's just kind of interesting what goes on here. Neither of these are necessarily optimal for all situations. So the right, you'd think, well, if you're have a limited amount of thrust you can output, you might want to optimize to get the most out of your system. So that's what the highest max thrust method is doing. But there might be situations where it causes undesirable effects. We'll see that a little bit later. But summary is there are literally an infinite number of ways you can map your torque and force commands to your motors, and so deciding on one is not simple. So now let's get back to the real world a little bit, where we have to recognize that we are controlling this with multiple vehicles, and they are communicating wirelessly. So the way we're accomplishing that is by assigning one drone to be the leader, and so it manages position control, and through its controllers generates an attitude set point, which it sends to all the other drones. So then all the drones share an attitude set point, and then they control that independently. A few add-ons to this are some simple transformations of the attitude set points based on the orientation of the drone, because they're just docked in different orientations. A more interesting problem is handling possible discrepancies between the attitude. If there's mechanical imperfections in the structure, and especially a case we're considering is if there's bending, because the drones are all pulling up on the ends of the structure, so there could be bending causing the drones to be tilted relative to each other. That's something that we've thought about, and we haven't. We've come up with some solutions for robustly taking care of this or addressing those situations, but we haven't implemented yet, just because it is a lot of work to do so. And it is flyable, nevertheless, with what we have accomplished so far. So this is showing just how that controller diagram I showed earlier is split up with the leader and follower system. And so it's just simply showing leader drone doing position control. And at the point where it makes its attitude set point, it will send to all of the follower drones, and they will independently execute attitude control. And right now you can see we're sending these at 50 hertz over the network. So the attitude set points are sent at 50 hertz, and that's because that's the default rate of this controller in the flight firmware. And so far that seems to be performing well. Now I will present some real flight tests. So that's exciting. We took baby steps and started with just 2 drones that were rigidly attached. So basically, the one of the smallest systems we could build to prove that this concept works. These videos are showing a comparison between the attached drones trying to hold position and comparing it to a single drone holding position. You'll notice that the drones attached to each other aren't doing quite as good a job as a single drone. And so luckily, there are a lot of things we have been able to improve since this very early test. So a few lessons we learned from what this early test is, well, one, that we did have adequate roll and pitch control of the vehicle, and so we were happy about that. However, we saw insufficient yaw control. So the top right is just showing an image of the motors the motor signals saturating due to just the drone not having authority over its yaw angle. And so with the help of one of our advisors, we decided to tilt all the motors, and this allows flight similar to if the motors are mounted normally. However, it increases the ability to generate torque in the yaw axis. So we decided on a tilt of 10 degrees because this was a good trade-off between being able to apply torque in the yaw axis and not losing very much thrust at all in the vertical direction. In fact, we get around a 7-fold increase in torque in the yaw direction, so that is very helpful. Additionally, we weren't super happy with the altitude estimation provided by the standard barometer and GPS, and one of our advisors recommended trying out a range sensor just so we have a better measurement of the distance to the ground. So that's another thing we added after this. So this is another test showing those measures in place. And so hopefully you can recognize a little bit of improvement. This also is showing the ground station on the left side of the screen. And I'll wait a little bit for video to get going. But the summary here is that the canted motors were able to accomplish good yaw control, and it was able to maintain a consistent altitude. Another thing this is testing is transferring leadership from one drone to the other. And so that's happening right now. You can see it dips in altitude a little bit. And I'll talk about that on the next slide a little bit. So just to clarify, when I say transferring leadership or leader transfer, I mean that the drone that is leading or doing position control and then sending set points to followers is passing off its role to a different drone. So in the case of these two drones, they're swapping roles. And so that's important to be able to do, as drones are going to be constantly docking and undocking to the frame. So we saw good success with that. But you saw the dip in altitude, which theoretically is straightforward to fix, but I think we need a little more testing to figure out if we've done that properly. As mentioned, the measures we took from after the previous test, like the canted motors and range sensors, were successful and did what we wanted them to do. We did the range sensors partly because we thought that it would be helpful if eventually we did docking in flight, if it was a little more stable in its height above the ground for the purposes of docking. Another thing to mention is that there's certainly room for improvement in tuning the controllers, like the PID gains and other parameters. This is just something that takes time, and we're certainly not experts at by any means. And so there's certainly ways where this could be bettered in software for control. So now let's move on to the 4-drone tests. So this structure is more than twice the diameter of the 2-drone tests, so it's quite a large upgrade. And so I'll show position hold again. Unfortunately, we didn't get too far past just testing position holds with this system. And these tests are relatively recent, and so at some point we have to say it's good enough. But you can see it's performing fine. On the surface, it's able to hold position. What you can see there a little bit is the drone shaking, and I'll talk about that in the next slide. And in a second, it will become a little bit unstable, and that's another thing to mention right there. So the lessons learned from this is that the motor allocation we were using was causing the drones to apply a lot of torque to the booms, causing torsion, and that led to oscillations around the booms. So that was interesting, but definitely something to expect. And I talked about the motor allocation before, and we think that the changing the motor allocation to something to the more standard one would help reduce that torsion. And so we implemented that before the next test. There was a software bug that limited our ability to make long flights here. So you're gonna get a whole lot of data. And additionally, the instability in this test was due to an abrupt yaw input from me controlling on the RC transmitter. And that's certainly something to look into. That just, I think, is pointing to the fact that the tuning of the controller could definitely use some work. So this is the last test I'm going to show, and it is another try at position hold with the structure. You can see that this flight was relatively short, and if you notice, the booms look a little bit out of whack or at different angles in this test. So that is because in a test just before this, there appeared to be an anomaly in flight. It could be we don't know what caused it, essentially. So we had a hard landing, and it actually cracked the center 3D printed support, and that caused a lot more bending in subsequent tests. One thing good about this test is that we didn't see nearly as much oscillation on the booms, so that was good to see. Additionally, we don't know exactly what caused a hard landing. This test was conducted last Friday, so we haven't had time to look at all of the data from this. But we do get a lot of data in logs generated on the drones, and so because of that crack in the 3D printed center support, we did accidentally reveal that it appeared that stability was good in the subsequent test. We didn't have that specific problem in the subsequent tests, and so we saw good stability even with that bending, which was good that the drones were able to compensate for that. We did see thrusts decrease shortly after takeoff. That's why the flight was short. That's another thing we have to look into. Obviously, flight didn't go as ideal as we had hoped, but that's the way things go. But we do have some data to look at to figure out what happened. So to conclude this section, do we have confidence in this rigid structure, or this mostly rigid structure, to fly stably? And yeah, we definitely do. We definitely demonstrated that we can fly and hold position relatively well up to a moderate breeze. And of course, that's my qualitative assessment of the wind on some days that we flew. But it would be nice to quantify the effect of wind or other disturbances. It's just something that's we don't have a lot of experience with. Additionally, obviously autonomous missions are one thing that we'd love to be able to accomplish eventually, which we didn't quite get to actually demonstrating something like a waypoint mission, but the proof of concept is definitely there. And I think if we do decide to move forward and work on this more, we could definitely accomplish something like a waypoint mission. I'll talk briefly about the communication system we're using. So all the controls code is kind of taking for granted that the drones can talk to each other all wirelessly with relatively low latency. And so the goal of the communications subteam, which another member worked on, but it wasn't able to come to present, basically the job was to provide reliable wireless communication between the drones. And we're using an ad hoc or a mesh network, which is decentralized. So there's no central router, and this provides a lot of flexibility. What we're using is optimized link state routing protocol version 2, or OLSR v2, which there has a corresponding RFC. There's an existing implementation of this that we're using, and essentially it operates on OSI layer 3, or the networking or routing layer, and it controls the network topology and manages detecting new neighbors that get powered on. So it will be able to adopt or change the network topology on the fly as drones enter and leave the network. This is a flowchart kind of showing the structure of the framework. I'm not going to go over this too much because I personally don't have much knowledge on what is going on here. So I apologize for that. I'm not sure if our networking teammate is here, but if he is, he certainly may be able to answer some questions. So we did do some tests separate from the drone system to just test the network, and we conducted some tests with different packet sizes and some interval around 5,000 microseconds between packets. So this is actually a very high throughput test, much higher than we're actually using right now in an actual implementation. And so what we've measured here is the delay time of each packet in microseconds. And so I'll just breeze through these graphs real quick. We're not going to analyze them a whole lot. But the conclusion is that for the larger packet sizes, like 2 kilobytes and 5 kilobytes, which are being sent at 5 millisecond intervals, there was significant packet loss. But this is just orders of magnitude more bandwidth than we're actually utilizing in flight. So it's just the disconnect between the sub teams. So of course this is good news. I think the performance we've seen from communications testing shows that it's definitely adequate for anything we might do in flight. One thing to mention is for the controls code, we're using ROS2 to manage communications, and so that requires working a little bit with the mesh network to make sure that it cooperates well with that. And so there are some measures we've taken, like disabling multicast for ROS node discovery, and that's not a super important detail right now. But the summary is we have configured ROS2 to act appropriately and work on the mesh network. Now I'll hand it off to Axel to talk about docking.
Yeah, so I will be talking about the docking subteam. Next slide. So the role of this subteam is to use the structures that Brugu and the airframe team constructed in order to determine and implement a process for getting drones to and from the system. So the general idea is to use GPS to get from the ground station to the general area of AVIATA, and then switch to a computer vision aided system for more finer control to dock, which needs pretty high precision. And this process is completely autonomous. So in terms of a general control flow, to understand what it is we're doing, if we could go back to the previous slide.
Yeah, lag.
Once we get the docking command, we'll take off and fly to the swarm using GPS. And then once we're within range of the swarm, we actually switch to that vision-based system. The reason for that is that GPS is not accurate enough to dock with the centimeter level precision that we need. And so therefore we have a bottom mounted camera that faces down, and there's a target near the docking joint to enable us to accurately control the drone. And so the general flow is to process an image, try to detect the target. We check the errors, and so by errors I mean the X, Y, Z, and rotational position of the drone relative to the target. If those errors are too high, so we're not within range, then we update a PID controller to adjust our velocity set points. If the errors are low enough, then we attempt to dock and then finally join the swarm. And so some technical context for this, the targets that we're using are called April tags. This was a research project at the University of Michigan to develop a visual fiducial system, which basically is artificial landmarks that enable us to get a lot of information, positional information from an image. And so an example of that is on the right. They kind of look like QR codes. We also created a simulation for this docking process in the early stages of this project, which was very useful for early testing and trying new things without needing to go out to an airfield and try untested code on a drone. And for that, we used Gazebo, which is a 3D drone simulation software. In terms of our physical environment, we have the Raspberry Pi 4 on the drone, which is what Ryan mentioned, and we're using the standard Raspberry Pi camera, and everything runs in C++. So the first problem that we had to solve with docking is the trade-off between target size and how far away we can be in order to detect it. The trade-off is that the target needs to be small enough to fit in the camera's field of view at close range, but also needs to be large enough to be detectable far away. Again, the GPS gives us an accuracy of about 2.5 meters, which we can reduce with RTK GPS, but we'll still need a certain level of detection, which is why we went with this two-stage docking approach. And so the idea is to have one large target in the center for the initial approach, and then close range targets on the periphery at the docking joints for the actual docking procedure. So then if we go to the next slide, we'll see the first stage of docking, in which we use the central tag to align close to the peripheral tag. The drone also rotates to be able to use the full horizontal field of view, which is greater than the vertical field of view. And then once we're able to detect both targets simultaneously, we can transition to the second stage of docking, which is just normal docking, in which we try to get as close as possible to the target in order to dock within the cone. And so that cone has about a 9 centimeter diameter, which gives us a fair amount of tolerance for the final stage. I also want to briefly mention failure handling. So failures will happen when the target is out of the frame of the camera. And after some testing in the simulator and as well as some real testing, we found that the easiest solution is to simply ascend to increase the area in each camera frame while moving towards the last detection. This does get very tricky with some unpredictable wind gusts, especially when we're really up close when centimeters matter. And so wind sensitivity is something that we've had to struggle with a little. Briefly, I want to mention an unsuccessful previous concept. We originally broke up our multiple stage docking into 3 stages, in which we would simply try to hover over the central target and then fly to the peripheral target. Unfortunately, that second stage was being problematic because we didn't have any feedback during flight, and so it was too unpredictable in getting to the third stage. So we decided to modify our first stage to use the central tag as a positioning tool in order to more smoothly transition from detecting the central tag to detecting the peripheral tag. And so here we have a quick screen grab of the simulation that we developed. On the left, we have Gazebo, the 3D drone simulation software. And then on the right, we can see it's a simulated camera, so we can see what the drone quote unquote sees from its point of view. And so right now we're seeing what the topmost drone sees, and it's attempting to dock with the bottommost drone on the left side of the simulation. And then on the next slide, we have some physical results to show as well. So in the left video, we have our 2-stage docking procedure. We place the central target and 1 peripheral target on the ground, and the drone right now is trying to find the midpoint between the 2 targets, which is stage 1. Right now you just saw it rotate, and it's actually transitioning to the second stage of docking and approaching the peripheral target. And once it sees that the errors are low enough, in this test right here, it was just trying to land on top of the target, but it was able to successfully do that, which shows helps validate that our multi-stage docking procedure is viable. And then on the right, we have the results of tuning the PID controller on the drone. So the drone was now precise enough to be able to autonomously land within the docking guide cone and then afterwards detect that it was docked. So here you can see in just a moment, it's going to push against one of the edges of the cone and then slides in pretty nicely and slots in painlessly. And then we move to the next slide. I just want to acknowledge that, this is nothing new, but we did do PID tuning for this control loop. So we extract X, Y, Z and rotational error relative to the tag, and then use that to update the velocity set points. You can see that there was a lot of tuning that needed to be done. Before we had very little stability, and then afterwards it does take a little bit of time to dock, but we are able to get those errors low enough to be able to dock with the precision that we need. So this kind of shows the improvement. I'm definitely not an expert in PID tuning, but it shows that it's pretty decent for our application. And then finally, the last thing that we've developed in terms of docking is being able to detect when we are docked. So we do this using a circuit controlled by the Raspberry Pi. On the left, we have a simple schematic that shows how it works. We have general purpose I/O pins on the Raspberry Pi, and the basic gist is that we output a voltage, and then if the switch is closed, then we detect it on the input pin, and that means that we're docked. Otherwise, if the switch is open, we detect nothing, and that means that we're undocked. And so on the right, we have the implementation of that. You see the Raspberry Pi on the top left in the yellow and blue case with the I/O pins. And then there's a purple and brown wire that comes out of the Raspberry Pi and goes through the middle of the docking adapter on the bottom of the drone. So following the vertical red arrow, those contacts are unconnected at the base of the docking adapter. And that circuit is completed when docked using the aluminum foil that we put at the bottom of the docking cone. So that is what acts as a switch. And so we actually tested that in one of the videos that you saw previously. And then in terms of testing milestones, docking-wise, we started physical testing once we finished simulations in January. And then in March, April, and May, we achieved some pretty significant milestones in terms of stepping stones to getting to the final product. Currently, up next, we have to test the final docking mechanism, which we've manufactured. So you can see here all the 3D printed components as well as the servo. And then all we need to do is assemble it and try it out. And then, yeah, so this is a little bit our conclusion, some possible future possibilities. So finishing docking testing, as well as getting an 8-drone system flying. And then once we get those two, we can finish the final product, integrate everything.
Sorry about the slides. There it is.
Yeah, so the final objective will be to integrate controls and docking for the final product. Cool, so that concludes our presentation. Thank you all for listening. We really appreciate your time and the opportunity to present our progress and results. And we should have a little bit of time for any questions that may have come up. Thank you.
Thanks. Yeah, we did have a few questions that came in during the presentation. One you answered kind of on the fly. I wasn't sure if it was on purpose or if you were just saying it at the same time. And that one was related to the RTK GPS positioning, which I guess you have considered because you did mention it kind of your reason why you leaned towards the process that you have now. There was a comment before I get to the multi-part question that John asked. The comment for John said the instability in the 4-drone tests could possibly be caused by the unmodeled structure dynamics of the airframe connected to the drones. We'll start with question 1 on John's 6-part question. And the first question was, what is the capture envelope for docking?
So I believe we showed that in the, did we show that in the mechanical airframe section?
Sort of. If you could go to the previous slide with the picture of the 3D printed docking cone.
Yeah.
Or the one before that, actually. I just wanted to show a few things. So the actual envelope is something we're kind of working on, assuming I'm understanding this question properly. But the way it works right now is there's the section that's attached to the drone. You see there's a small alignment feature at the bottom. That's sort of an egg-shaped alignment feature. And there's a corresponding egg-shaped recess in the bottom of that cone. So the first step is sort of those two aligning, and then you sort of drop into that bottom section, and that's where the electrical contact is formed. Then the cylindrical section above that, There's a cylindrical section in the in the bottom cone as well, with sort of ridges that pop out on the top section and then corresponding recessions in that bottom section. Those are to sort of lock up the rotation about the central axis, so to speak. And then there's the final step, which is not present in this one, but those electrical keys which are pushed out in, this is a slide that we showed earlier in the mechanical section where the 4 keys are sort of pushed out by the servo into those 4 corresponding platforms. So right now the way it works is sort of just friction and then contact force based. We would like to look into some more advanced capturing techniques like using maybe ratchets or some sort of bistable spring mechanism or some other sort of system that has a more solid lock than the one we have, which is just sort of cutting off all the different degrees of freedom. And yeah, if there's any advice you guys have for that, we'd look forward to hearing about that, because we were having some trouble trying to finalize that during our design process for sure.
And John also goes on to ask a few questions just about how the control allocation changes during docking, or how it switches, and how the vehicles are controlled when docked, if it's independently or not.
Yeah. So the first part is a good question, and so with the help of our communication system, we can send messages between the drones, essentially very flexibly. And so when a drone does dock to the system, it will send out an announcement as soon as it knows that it's docked to the rest of the drones, and then they will all update their control allocations to accommodate the new configuration of drones that is on the system. And the same thing happens when a drone undocks. So as fast as possible, we send messages to alert all of the drones of the state of each other, so they know what's present on the system and what the dynamics will be. And for the second question on if they're independent, yes and no. I suppose the more correct answer is yes. So if we're talking about attitude control, the drones are doing attitude control independently. There are some improvements we can make to make them a little more collaborative in that, and I'm happy to elaborate on that if you would like. But what the drones don't do independently is position control, and instead we just have one drone doing position control, and it's the attitude set point is sent to the rest, and that is independent.
Thanks. Yeah, I don't know if we have time to get to all of those 6 questions, but if any of you on the team want to answer some of the ones that we didn't talk about while we head to the other questions, that would be great. He did comment though that there is some NASA work relating to linked aircraft, both multi-rotor and fixed wing, that might be of interest if you haven't already looked at it during your research from NASA.
I don't think we have, so that is good to note.
Yeah, John, if you could still hear us on the line, if you have any links to those, that may be great for the team to have access to. Another question was asking how long will this project continue for? Is there any plans to transfer it beyond you all if you all aren't able to finish it, I guess, during your time as students? And also if you plan to present any of this research at upcoming national conferences.
Yeah, so I can answer this one. We don't actually currently have any plans to present this anywhere else. So a lot of the results were actually very recent results. And in terms of the future of the project, unfortunately, we actually just graduated this past week. There are some club members in UAS at UCLA who are continuing, and so we're planning to write up documentation for everything that we've done so far. So the project should hopefully continue in some capacity, and so yeah, in terms of transfer of knowledge, that's what we're planning to do, but we're not really sure of the scope of that transfer yet.
Thanks, great. And if you have seen John reply to the chat, that he will be able to share with you some of the links from the papers he mentioned. So hopefully you all will find any of those useful.
Great, thank you.
Do you all have it seems some people are interested in maybe hearing more or following the project. If you have a website for the team or any links you could provide for them in the chat, that might be a good resource for some of the people on the line who want to see what's going on after this presentation.
Yeah, I can actually post our club website, and so we've been posting regular updates about the project there. So in just a moment, I'll be able to get the link.
Sure. Kind of as a closing out, if anyone has any more questions they want to post in the chat that might be able to be answered by the team after the presentation, after we close out, please do so. If not, you can reach out to them probably through their website or through any email they might provide in the chat if their website doesn't have any way to reach them. Once again, thank you for tuning in for today's USRC Tech Talk, and thank you to the great AVIATA team for presenting their interesting work. If you have any questions for them or me as the USRC point of contact, please feel free to contact any of us, or if you'd like to get in contact with the team, let us know if you have any issues contacting them otherwise. Please see the chat if you have any want to see more information on USRC or for any interest for signing up for future USRC talks. This talk and other talks are posted on our website, so feel free to watch this later, share it with others, or see other presentations that have gone on. Anything last words from the AVIATA team before we close out?
Just another thank you for all showing up and listening to our presentation. This was great. Thank you.
Yeah, thank you. We really appreciate we appreciate the interest in the project.
All right. Well, thank you. Have a great week, everybody.